Welcome everyone. It's a great pleasure to have here Professor Anjan Sen today. Thanks a lot for accepting our invitation. Anjan is professor at Jamia Millia Islamia Central University in New Delhi in India from 2007, while he did his PhD at Jadavpur University, always in India. He then joined as a postdoc the Harish Chandra Research Institute in India, the Istituto Superior Tecnico in Lisbon in Portugal, and then Vanderbilt University in the USA. Today he will present Decoding Cosmic Mysteries, Unorthodox approaches towards new physics. Anjan, please, you can start when you're ready.
Yeah, I'm audible, Eleonora?
Yes, perfect.
Yeah, okay. So thanks, Eleonora, for this invitation and giving me this opportunity to present some of my works that we are doing in our group. What we'll do is basically some of this, I call it unorthodox because it's not some very popular approaches that people are using nowadays to see whether there is a new physics in this cosmological data. So I'll talk about two ways that we are actually approaching toward this new physics from cosmological data. Okay, so I'll start with this basic notion of our expanding universe that we know that at the very early time that we have some inflation, accelerated expansion at the very early beginning, then the universe is decelerated by the dark matter, and then around the present time the acceleration of the present day universe has started, which is predominantly because of the dark energy, or if there is any modification of gravity at the cosmological scale. And this is basically the expanding universe that we are studying. So it's given by a FRW universe, which can be spatially flat when this K term is 0. And A is the scale factor is actually the dynamics. I mean, all the dynamics of the universe is governed by mostly by this scale factor. And so in a sense that it's a distance, it measures the distance between galaxies. So we have its two time derivative, what is related to the velocity, which is the expansion rate of the universe, and another is the double derivative of the or the acceleration rate, which is we call the deceleration parameter. And this expansion rate is related to the total energy density of the universe. So as we probe the expansion rate to supernova type 1 supernova or BA measurement or this cosmic chronometers, we are actually constraining the total energy density of the universe. On the other hand, this acceleration rate or deceleration parameter, which we can probe through again type 1 supernova or BO measurement. These actually constrain the energy density plus the 3 times the total pressure of the universe. It's sometimes called the ADM. If you go to the part of universe, then this delta M is basically the density contrast, the deviation of the matter fluctuation from the background homogeneous isotropic matter. And then we can construct few observable. One is the growth factor, which is the F, which is the logarithmic derivative of this delta in terms of the log A, which we can measure maybe in the next Euclid observations. You also have two more parameters. One is the redshift space distortion parameter, which is the F sigma 8, where sigma 8 is basically the variance of this density fluctuation at 8 H inverse megaparsec scale, which we can probe through BAO like measurement like DESI or SDSS, or in the future Euclid measurement we can probe. And another is the S8, which is actually related with the weak lensing shear distortion amplitude. This is related with the total matter density and the sigma 8 parameter. And this we can measure through different weak lensing measurements like KITS or DES or Euclid. So this is at least at the linear scale or the deviation, which is up to the linear order of the perturbation. And there are various observations, as we all know. There can be nucleosynthesis result data coming, then there are CMB fluctuation, then there are all the galaxies that we probe from different redshift surveys. We can have their growth histories. We can have the probe through lensing or weak lensing. Then there's type 1 supernova, there baryon acoustic oscillation measurement, where we have also the redshift space distortion parameter, which are related to the peculiar velocity. So if you put all these observations, and we all know that and then we have this Planck 2018 observation, which is the crucial observation that we have. If you put everything together, we all know that this concordance lambda CDM model is basically the best model that fits mostly all of the observations. And this model is a 6 parameters model, assuming that the dark energy is given by the cosmological constant. And these 6 parameters are actually put in here. So there is the amount of baryon we have, amount of cold dark matter we have. Then there are 2 parameters that is related to the primordial fluctuation, which is given by the inflation. Now, one is the amplitude of this fluctuation, another is the sort of the scale, what is called the spectral index, or the slope of this fluctuation. And then there are other 2 parameters. One is related to the acoustic scale, and then another is the tau, which is the optical depth for the reionization, which actually govern the decay of this fluctuation at the small scales. Fine. So these are the fitting parameters, and from these fitting parameters, we can derive other cosmological parameters like the Hubble expansion rate at present, the sigmoid parameter, the S8 parameter, the omega m parameter. Okay, so these are the derived parameters. So in the ΛCDM model, at least given this model, we can have these 3 parameters up to the linear order fluctuation, which is the matter density at present, the Hubble parameter, expansion rate of the universe at present, and sigmoid, that we can measure to the Planck 2018 observations very, very accurately. And we also put the other measurements like supernova or DONTs, and we can get a very strong constant on these 3 parameters. So what is this lambda? So we all know that Einstein introduced it in 1917 to make a static universe, but actually the energy momentum tensor of a lambda coming from Black-Long fluctuation of field theory, that is first given by this Zeldovich in a very interesting paper in 1968. And it actually says that this energy momentum tensor have an equation of state which is -1. But we know all the problem is that the observation demands a value which is much, much smaller than what the theory gives. I mean, assuming that we have a standard model of field theory. And so in that sense, this cosmological constant that we all constrain through all the observations, this number or this cosmological constant has no relation to the physically acceptable field theory. So it's just a phenomenological model that we have. And we introduce it in the Einstein's equation, and we get its number through cosmological observation, which is around 10 to the power minus 47 GeV to the power 4 in terms of lambda by 8 pi g actually in that sense. So what is this concordance ΛCDM model? It's a phenomenological fit. It has 3 main ingredients. What is the cold dark matter? We still don't know what is cold dark matter. It has lambda as a dark energy. We still don't know what's its origin, why it is so small. And also it has another input which comes to the inflation, which is the scale, nearly scale invariant primordial power spectrum, which is given by this kind of a power law power spectrum, and two parameters AS and NS. Still, this is a very phenomenological fit. Fine, we can take some scalar field, but in actual case, when you're doing the data fitting to the Planck, we just assume this this power spectrum. Fine. And we don't know what is this interferon field. So ultimately, this ΛCDM model with this primordial power spectrum plus this H expression, this should be H square, H expression is just a fitting function. And surprisingly, this fits almost all of the cosmological observations that we know of, whether it's a CMB, whether it's a BO, or whether it's a type 1 supernova. And it's a very amazingly well fit. But we all know now that in recent years, there are tensions that are coming up in this cosmological constant or ΛCDM model. One is the Hubble tension, where we have the measurement of the Hubble parameter to the local measurement, as Hubble did in 1930s, which actually depends upon the astrophysics of the stars. It doesn't depend upon the cosmology, okay, mostly. And it's a kind of model independent. When I say model independent, it's basically model independent of the cosmological model independent. On the other hand, as I showed earlier, that the Planck, assuming a ΛCDM model, can give a very strong constant on the H0 parameter. So this measurement depends upon the physics of the early universe, and also assuming there is a ΛCDM model. And we all know that these 2 measurements are now in tension around 5 sigma, 4 to 5 sigma. Fine. We also have, so this is the now current status. This is the slide that I took from the recent paper by Dan Sklonik, where not only this shoes measurement, but there are other local observations which are all actually in tension with the Planck CMB measurement. Right? And also we know that there are S8 tension, which is basically that the S8 parameter that we measure from weak lensing from different surveys like KIDS or any other surveys that we have over here. And this value that we measure from Planck, assuming a lambda CDM model. So again, this is a derived parameter for Planck. And these two measurements are roughly around 2.5 to 3 sigma kind of tension. Fine. So there are issues coming out in the lambda CDM model, even if it's a very fantastic feat of most of the cosmological observations. So what happens when one deviates from lambda CDM? Okay, and we in the literature we all know that this deviation is mostly we parameterize through the CPL parameterization. It's a 2-parameter parameterization. It's a very nice parameterization in a way that it also actually represents a large section of dark energy model, which is we can make through the scalar field models. Initially, when the Pantheon Plus data came, so they have this this plot in the W0 WA plane, and as you can see at that time itself, the lambda CDM model was just at the boundary of the 2 sigma. Fine. But now we have more accurate measurement after DESI DR1. And depending upon what kind of supernova data you use, whether it's Pantheon Plus or Union 3 or DESI Y5, this lambda CDM model is out up to 2 to 4 sigma, fine, 2.5 to 3.9 sigma. Not only that, the interesting part is that the parameter region that is allowed now is basically showing that in this parameter region, the dark energy is at least at the late time is a behavior which says that it has an early phantom behavior and a late non-phantom behavior. Fine. So there is a phantom behavior. Not only that, there is a phantom crossing also. So these parameter space actually represent that. In a way, this is interesting because we have to now see that how this phantom behavior can be incorporated. So in that sense, there is a new physics in that. But the question is that whether this is really a new physics beyond lambda CDM or there's an artifact for the CPL parameterization. Fine. So that one has to see because these results come from the CPL parameterization. So for that, so this is another way that I said that unorthodox way. So we do a defined kind of parameterization. So we all know, as I said earlier, that when you take the basic data like BO measurement or the supernova measurement, the growth measurement, or in that sense, the CMB acoustic scale measurement, these are all mostly depend upon the Hubble parameter. So we can write the Hubble parameter in different way, like this can be interacting dark energy model, this can be a modified gravity model. But once we know the Hubble parameter, we actually, in the data or on the observable, it actually goes the Hubble parameter as a function of Z. Fine. Now for the lambda CDM, the scale factor, at least for the late time, we can write it analytically, fine, assuming that there is a matter which scales like 1 plus Z cube, and there is a lambda, which is a constant. We can solve or integrate the Hubble equation analytically, and we can write down the scale factor like this, fine. This is the analytical expression for lambda CDM. Now, one of the easiest way to go beyond lambda CDM is just to modify the scale factor, and we just change this 2/3 to some parameter d, fine, and just to see that what kind of d is allowed, fine. So this d is 2/3 is lambda CDM model, fine. Now, if you take the scale factor, we can write down this Hubble parameter. If we again put b equal to 2/3, we get back the Hubble parameter for standard lambda CDM model. But then, if not, this d is something else. This is a Hubble parameter, modified Hubble parameter. This can be actually written for a different way. One can write this as a dark energy model with a matter part, and there is a dark energy part. One can write it as a modified gravity model. One can write it as an interacting dark energy model. Whatever way one can write this expression, fine. But let's assume that we have this Hubble parameter and we write it as a model where we have a matter part and as a minimally coupled dark energy part with an equation of state, fine. So we feed this model with at least the late time data and try to extract that what is the dark energy behavior, fine. So we just try to extract what is the W0 and WA parameter plane for this kind of Hubble parameter, which represents a minimally coupled dark energy model, fine. And this is the result, fine. So this blue part, this blue contour that we have, this is the usual, if you use the CPL parameterization and use the DESI plus Pantheon plus and the growth data. So this blue part is basically the parameter space that you get from the CPL. This is the usual correlation that you can see between the W0 and WA. But if you use this behavior, this H behavior, and and take the dark energy behavior out of it and calculate the W0 and WA, you get this green behavior. Now, as you can see, these green contours, the correlation between W0 and WA is completely different than what kind of correlation you get for CPL. Not only that, like this region of parameter space is mostly in the completely quintessence region, whereas the CPL can go to a region where we have the phantom behavior. And also the constant is much tighter than the CPL, fine. It's not that this is actually the universe is, but it actually shows that we can take a very simple generalization of the lambda CDM, not like CPL, but some different way, and we can get completely different results actually. Now, we can actually get the behavior of the omega matter and omega dark energy. So the right-hand side is for the CPL, the left-hand side is for this our general model. As you can see, both omega m and omega dark energy, the omega m goes to 1 at early time, where omega dark energy goes to 0 at the late time, just like CPL. Only thing is that in this case, the omega m goes to 1 in the early time, a bit slower than the CPL parameterization. Similarly, omega dark energy goes to 0 in the early time, slower than the CPL parameterization. But it does go to a matter-dominated region. So there is no difficulty this model to extend to a matter-dominated region and then to the radiation region, fine. Also, interestingly, this kind of parameterization, as you can see, also allows regions of parameter space, whether you take it a physically available viable region or not, that there can be region in the parameter space, at least at 2 sigma, where the omega m goes to greater than +1 and omega dark energy goes to less than 0, fine. So that possibility is also there. But overall, this model is actually goes to matter-dominated region in the past, and also if you put the radiation, it go to the radiation-dominated region. We also just to see that whether how is the evidence of this model. So if you just look at this column where we put the evidence, so the joint means that we have the DESI data, the Pantheon plus data, plus for joint 1, we have the growth data, joint 2 also the growth data, but joint 2 is basically DESI replaced by the SDSS data. So the joint thing is basically the DESI, Pantheon plus growth, or SDSS, Pantheon plus growth, same for CPL, fine. And as you can see, the evidence between this model, our model, and this CPL, is absolutely they are equally viable model. There's not much of a difference between the evidence between these two models, fine. A bit slight improvement of evidence in this general model, but that is very small. Otherwise, there is no difficulty in between this model. No evidence means these two models are completely viable. Fine. So this is one nice example just to see that that if you go to a different parameterization, one can get some different results actually regarding the dark energy behavior. Fine. Now, what other new physics you can have in the dark energy sector after DESI? Now, there's a very interesting paper by Tada and Terada. It came to Physical Review. What they did, as I showed, that in the DESI result, so there is a late non-phantom and early phantom. So they try to see that at the late non-phantom region, where we actually can model this dark energy behavior through a scalar field at the late time. So what is the scale, what is the potential behavior for this late non-phantom? Okay, so they take the base feed values of this DESI and then show that now if I assume that at the late time when it's a non-phantom behavior, I model through a scalar field with a potential. The potential is basically this, okay, and if you kind of around this region, if you just zoom it out, you can see there is a small deviation towards the negative value of the potential. So potential does have a minima, which is actually at the ADS minima, so that there is a negative minima of the potential, fine. So this is and this is from the DESI chain fixel, fine, DESI base fit number, fine. So this is also a very interesting results, fine. Now, there is also another paper after the Deci result pen. These are basically string theorists. So they actually constructed a potential from some holographic CFT, and the potential has a ADS minima. And they say that, okay, let's assume that the universe is very close to this minima. So I can expand the potential up to the linear order, fine. And here, V1 positive means basically you are going to the negative part. So they are actually assuming the phi to be negative. Okay, that is fine. So V1 is 0, then V is V0, that is a lambda CDM model. And V1, if V1 is positive and non-zero, this actually shows the potential is actually at the minimum. I mean, it's at the negative minimum. And then they use the supernova Pantheon plus data, and then they add the BO data from Deci. And what they show is that when they add the BO data from Deci to the supernova data, the lambda CDM obviously is ruled out. Not only that, the parameter span region is basically where V1 is basically non-zero. Not only that, V1 is positive in a way that the potential is actually has a negative minimum, fine. So this is also interesting, is a kind of a hint that I can have models where the potential can have a negative minima and which can be consistent with the current data like supernova, Deci, and other things, fine. So what is this? So in general, when you model a dynamical dark energy like CPL, we usually put that the universe doesn't have any cosmological constant. So the dark energy is just like a CPL parameterization where it has, if it means there is no cosmological constant in the theory, fine. The whole cosmological constant is replaced by a dynamical dark energy, which usually modeled through CPL parameterization. Now, if I take a scalar field as dark energy, this means that the minimum of the potential has to be 0, fine. And there is no reason in principle that why the minimum of the potential has to be 0, fine. I mean, there is a priori no physical principle that says that the minimum has to be 0, fine. Also, there can be a bare cosmological constant, like what Einstein had in very early time to make the universe static, fine. So there can be a bare cosmological constant because the Gini mu term is a covariantly conserved term. So we can always add a lambda small Gini mu term in the T mu. As well as we can have lambda from the 0-point fluctuation from the each field theory degrees of freedom. Okay, so that is always there, like what I showed that Geldovic shows that we can have a term like lambda delta nu term, okay, coming from the vacuum fluctuation or 0-point fluctuation. So in a way, if you say that we have no lambda or we put the lambda equal to 0 by hand, we said that all these contributions are somehow cancelling each other to make the effective lambda exactly 0, and that can be a very strange coincidence, right? I mean, it can happen, but it's really a strange coincidence that all these lambda terms that is coming from either from the scalar field or bare lambda or the 0-point fluctuation, they are of different signs and they cancel each other, fine. Otherwise, we can have an effective lambda that can be either sign, that can be a positive sign or negative sign, depending upon how they cancel each other, fine. And if we believe that the string theory is a correct theory of gravity, then lambda less than 0 is much easier to construct thanks to the ADS CFT correspondence for the same string theory. And also there are conjecture like swap-Planck conjectures and others that which says that a de Sitter means a theory like positive cosmological constant is very difficult to construct to string theory, whereas a model like with a negative cosmological constant is easier to construct. But now if we have to construct a sort of a model where we have a presence of a negative cosmological constant, we need to show or we need to find out that how this negative cosmological constant has to be a very small number, because ultimately we are putting at the late time and we don't want to put any extra energy scale in the universe. So that should be of the order of the present day energy density. So this negative cosmological constant that you have to put in your model or in your theory has to be very, very small, whether there is any example of that. Now, fortunately, there's a recent work by, again, these people, they're all sort of from the string background. They wrote a physical review latest paper, and later they wrote a more bigger paper in physical review D, where this model has problem. They also mentioned there's some problem, but at least they managed to construct a model where they obtained a cosmological constant, which is of the correct value that we want to have, and which is negative, right? So this is possible in a way that one can get this kind of negative cosmological constant with the correct energy scale. Okay. So then we try to find out that there is a kind of a again in an unorthodox date time modification. What we did is that we put a negative cosmological constant in the dark energy sector. So the total dark energy density is rho phi, what we have, whatever, the scalar field or any other field, and then there is a cosmological constant, which is negative, fine. So the rho phi, or the equation of states for this phi field, can be, we can write through a CPL parameterization or a constant. It can be a constant, fine, like normal WCDM model. But now the whole dark energy has also a extra negative cosmological constant part. This is the acceleration equation, which is just modified by this addition of this 2 lambda term over here. And the dynamics of the linear matter fluctuation is remain the same, because the lambda doesn't change, because it doesn't have any fluctuation, fine. So only thing that changes here is the H will be now replaced by this term, where now have extra cosmological constant sitting over here, fine. Otherwise, this equation is the same. This is a thing that we just finished. We are more or less wrote the paper. Maybe it will appear another next couple of days, fine. So it will be great that we can have some good comments or some criticism of this thing. Okay, so we use now just to see that if we take this kind of model, what this addition of this all negative cosmological constant is actually give us, fine. Whether it helps us, it make the matter worse or whatever, fine. So we use the data from Planck 2018, including the lensing. We have the BO data, the first year DESI DR1 data, fine. The Pantheon plus data, plus including the calibration that we can get, we have from shoes. And we also use the weak lensing data from KITS 1000, fine. So these are the data that we are using, fine. Now let's see that what it actually does, the introduction of this small negative cosmological constant. So this is basically when we just take the Planck and the DESI results, fine. The right-hand side, the WCDM is the usual WCDM model, and when we say CC, that means we are adding a negative cosmological constant here. Similarly, for CPL, CDM is the usual CPL model, and CPL CC CDM that we add a negative cosmological constant. So as you can see that there is not much of a change in the W0 H0 plane. Whatever we have the CPL from the DESI results is basically like that. Only thing is that this is the shoes error bar, fine, for the H0. So there is a region of parameter space which is consistent with the shoes error bar, fine. Only difference is that if we take, let's say, the WCDM or WCC CDM, the region where the shoes error bars are, I mean, like is consistent with the shoes error bar. For the WCDM, the complete region is basically non-phantom, but there is a small non-phantom region when you add the negative cosmological constant, fine. Here also the same. There is a very tiny place over here at the non-phantom region, which is consistent with the shoes error bar. But if we add the negative cosmological constant, this region actually get a little bit larger. Okay, so that is the only effect of this negative cosmological constant. Other than that, the things are kind of same. So what you can see that that these things is this CMB plus DESI is consistent with the shoes error bar, fine. So we can add shoes data on top of it. This is with the S8 and H0. Again, is basically the same, both this case, whether you add cosmological constant or not, for WCDM, WCDM, or CPL CDM, or CPL CDM. Only thing is that the correlation between S8 and H0 is that if you go to a higher H0, your S8 actually decreases, fine. So that helps. So if we can manage to get a higher H0 value, your S8 also goes down, and that also helps to be consistent with the kids number, fine. So that's the thing that we can see. Okay, so this is with the Planck 18 and DESI. This is the W0 WA plane. So this dot dashes line is the W0 plus WA equal to -1. Anything above that is basically we can have a non-phantom behavior. As you can see, whatever we know from CPL result after DESI, that this result is that already lambda CDM is ruled out. Not only that, the region is basically a early phantom, late non-phantom region. With addition of the CC, things remain the same, but only interesting fact is that now we can have a region, a very tiny region of parameter space still there, which is actually satisfies the weak energy condition, fine. Okay, so that is in a way is helpful to go to a quintessence region, fine, which we don't see in the CPL, fine. Okay, so given that we all these results shows that this the Planck result plus DESI can give you a region of parameter space which is consistent with the shoes. So we add the Pantheon plus the shoes, fine. And as you can see that the region is there. Obviously, the region gets shrunk a lot. Still, there are region in the parameter space, okay, both for the WCDM, WCCDM, and everything that is consistent with the shoes result, fine. So that part is there. Only thing, again, the thing is that if we take the constant equation of state, then for WCDM, the region which is consistent with CDM is completely in the non-phantom region. But for WCDM also, now the region goes to the non-phantom region, in the phantom region. But if you have the CPL models, there is a region in the parameter space where it is still, which is consistent with shoes and everything, but still the region is actually in the non-phantom region. Okay, so that is one observation. So this is now taking into account for the WCDM and WCCDM. We take this is the gray area is basically from the kids. So everything is now consistent with the kids. The consistency is better if we add the negative cosmological constant over here. And also as I told earlier, as just showed earlier, that there is a region of parameter space which is consistent with the shoes type. Okay, so WCDM, WCCDM, there's not much of a difference. Only thing that the region where the parameter space is consistent with the shoes a little bit larger in the context of negative cosmological constant. If you go to the CPL and CPL CDM, again, exactly the same. There's not much of a difference between CPL and CPLCC when you add the negative cosmological constant. Again, the region of parameter space that is consistent with shoes is a little bit larger, not that much, fine. Now, again, this is with the PP, means P18, DC, and Pantheon plus, and this is just we add the shoes. Again, things are, so as you can see, for the CPL parameterization, both are a kind of thing that you add shoes, it goes a bit little down, right? But still, if this would take this is the Pantheon, the DC results. So this region is completely in the non-phantom. But again, if I take this W0WA line, still, at least when you add the negative cosmological constant, there is a region of parameter space which is actually satisfies it's a non-phantom region, fine. It is satisfied the weak energy condition. So we try to find out what this region is, what this region lies, okay. So this is the region that because in the omega lambda and W0WA, okay. These red contours are when we have P18 deci plus PP, when the blue contour is just the P18 and deci. This dotted line where omega lambda is 0 is basically the CPL line. Okay, this dotted line is basically the CPL line. And as you can see, if you take the CPL line, then the region where the region actually goes towards the phantom region, fine. But if you allow the cosmological constant to be negative, then we have a region of parameter space over here, which actually satisfies the weak energy condition. So in a sense, the only help that the negative cosmological constant is actually giving on top of CPL, other results are completely the same, is that it helps you to get a region which is consistent with the non-phantom behavior, fine. So we try to find out from a chain, we take all the chains, take the 2 sigma confidence level, all the chain, and try to put this constant that W0WA is positive, W0W is greater than -1, W0 is greater than -1. So all the non-phantom sort of constant plus the omega lambda is negative, fine. And these are the equation of state. So this is the part which is actually evolving omega phi. And as you can see, so there is we get a considerable amount of behavior putting this constant around 2 sigma, where the equation of state for this part which is evolving, which we have to model in principle from a field theory, is completely non-phantom, fine. And this is the part where we now with this part, because our dark energy is not only this part, but the dark energy is this part a negative cosmological constant. So if you calculate the equation of the total dark energy, then as you can see that there can be region where the total dark energy can go to phantom around the present time or in the early time, but there also can be behavior where the total dark energy is completely non-phantom. Fine. So again, the benefit of having these ADS in the dark energy sector is just the fact that it doesn't change anything from the CPL, but it gives a parameter space actually where we can have completely non-phantom behavior. Okay, so this is one of the really interesting implication of having an ADS or a cosmology, negative cosmological constant in the dark energy sector. So this is the evidence that we have calculated for our model compared to when there is no cosmological constant. And as you can see, whether you take WCDM and WCCCDM or CPL-CDM or CPL-CCCDM, there is not much of a difference. The evidence is roughly the same. The difference of evidence is much, much smaller than one. Fine. So this means adding negative cosmological constant doesn't make your fit worse. The results are more or less the same like what we have for the CPL, but the advantage that you gain here is that you now have a parameter space where the dark energy can be modeled as a non-phantom behavior. So it is much easier to model now through a scalar field which satisfies the usual field theory constraint. Fine. Now, what is the other implication of adding the ADS? Fine. So this is another interesting part. I just tell very shortly is that that this we have calculated. This paper came recently in the Astrophysical Journal. What we try to find out that what is the implication of adding this negative cosmological constant in the dark energy sector, assuming that there is this JWST result. So we all know that now the JWST have observed some of the very, very bright galaxies at a very high redshift, which is very difficult to explain within the standard lambda. If you assume the standard lambda CDM cosmology, fine. There can be a lot of astrophysical implication with that. But if you say that, okay, I mean, astrophysics remains the same, and my cosmology standard lambda CDM cosmology, the things is very difficult to explain this excess JWST bright galaxy. So we want to try to find out what this negative cosmological constant can help, or is there any implication of that? So this is a plot where we just, I mean, this paper is there in this journal. So we just show a plot where we just show this the evolution of the the UV luminosity density, assuming that we have a negative cosmological constant. So the line means as you can see that as you go to the black region, and this line, the boundary, this is the cosmological constant, lambda CDM model, fine. And as you go up, so your cosmological constant going to the negative value, fine. So these are the data points, fine. And so as you can see that as you go to the higher redshift, they are coming up some data points which are observed by this JWST telescope, which actually cannot be explained by the standard lambda CDM, which is just at the boundary, fine. But as you add negative cosmological constant, the implication of this is actually explained in this paper. So for a shortage of time, I don't want to go that, but you can ask me, I can explain it later. But what this negative cosmological constant gives you a kind of a bump around the redshift range where you have these data. And here we use the number W0 means this is just one such number, which is consistent with what we get from this CMB plus DESI plus Pantheon plus, fine. So whatever the number that we gave, the constant we get, we take that one of the numbers. You can choose any number within that. So this is the number that is allowed within the 2 sigma parameter region. And this is the number, the cosmological constant value that is allowed also within the 2 sigma parameter region. And what it actually shows that with these things, so that the model is already constant by the CMB, DESI, and PP. Within that constant parameter space, if we can calculate this UV luminosity density, it actually gives a bump that actually can help to explain these excess JWST bright galaxies without changing any astrophysics that we actually know of. Fine. There can be other astrophysical implications, but if we keep our astrophysics intact, then just solely the presence of this negative cosmological constant can help to sort of explain this kind of excess in the JWST measurement, fine. So it has very nice implication actually in other, I mean, not only in CMB or in supernova or DESI or BO data, but also in the galaxy data also, it can have some very nice implication. So I just summarize. So the lambda CDM has been a very successful model, but despite it has some theoretical challenges. But we all know that recent results from SHOES or DESI, DS or JWST, there's some tensions are coming in the lambda CDM. And most of the time, we parameterize this deviation from lambda CDM using the CPL parameterization. And all the speculation of new physics are mostly based on this parameterization. That, as I showed, that there can be other parameterization that can lead to different conclusions. So one has to be a bit careful about using CPL parameterization and sort of study the new physics. That other thing that we have that already in the DESI results that we have that if there is a new physics, the new physics says that there is a phantom region in the early time, fine, early era, fine. And we all know that the modeling a phantom is not a very easy way, fine. It's very difficult because it leads to ghost in normal field theory, fine. But what we are showing that if we add a small negative cosmological constant in the dark energy sector, which is theoretically motivated, it's not that we can just add it, but it is theoretically motivated, then it gives an implication which is interesting in a way that now we can have a region of parameter space where the non-phantom behavior is completely consistent with the observational data, okay, including DESI. So that's the advantage of using or putting or adding an extra ADS sector in the dark energy. And also, as I showed, that it has also other implications like the JWST observations, right? So I now thank you with that, and I can take any questions.
Thank you. Thank you for the very nice talk. Do you have any questions? I see a comment in the chat, but I think Owen is not here anymore. There is written W0 inferences seem to be the same. WA inferences are model dependent. I don't know what he's referring to.
Yeah, means I agree that means I mean, if you take any other parameterization, the inference of WA changes, and that's actually what we showed in with a different parameterization. So it's true. Means I agree with this comment from Ion, but I don't know whether he's still there or not.
Thank you. Do you have any questions or comments? Can you go to the slides where you are showing the first paper, the one
Just a moment.
with the scale factor parameterization?
Yeah.
Okay, this one. Okay, can you go back 1 second? So here what you're doing is actually you're changing the equation of state of dark matter as well, not just dark energy, right?
No, because we get this H. This H you can write as a omega m, which is 1 plus z cube, plus a dark energy behavior, fine. So this H can be written in a different way. In our paper, we actually mentioned this H can be written as a modified gravity model. It can be written as an interacting dark energy. H can be written like a dark energy plus a dark matter model, which is minimally coupled. So there is no coupling between dark matter and dark energy. So I can take out the omega m into 1 plus z cube part from here, and the rest I can say that this is the dark energy. Okay, so this is the general, because once I write this A is not the matter, fine. A is not a matter, fine, or A is not a cosmological constant. This is an expression for the H. Now, how you interpret this expression of H, it's up to you, means what kind of interpretation you have, whether you interpret as a dark energy, dark matter model, or a modified gravity model, or interacting dark matter model, dark energy, dark matter model, that's up to you. But we can use, when we do this, when you do this thing, we assume that this H represents a matter plus a dark energy with a variable equation of state, and matter goes like 1 plus z cube. Yes.
Okay, thank you. And okay, I think there is a typo in the equation, so like one of B.
This should be beta B actually. Yes.
So do you have the constraints on beta for this model?
Yeah, we have. I mean, I don't have the slides over here, but if you go to this paper, we have the constant on B, and this B constant is different from what you need 2 by 3. Yes, because I have yeah. Look at this table. So I have this table over here. So if you said that when you have this region, let's say this is for the Deci plus Pantheon plus whatever the growth, and this is SDSS plus Pantheon plus growth. So as you can see, so yeah, so these are the constants that you can get actually.
So you are ruling out lambda good matter.
I mean, if you take it depends upon what kind of. So if you use SDSS, yeah, it is ruled out at a good number of sigma. If you take let's say Deci, it is sort of around 2 sigma. It's ruled out, so roughly.
Okay, thank you. And Amari?
Hi, thanks. Does that parameterization explain all the expansion history, or is it only for late time?
Which one? Which part? Can you again repeat?
The scale factor parameterization that you just showed us.
Yeah. Okay. So these at this moment we are doing for a late time behavior, but as you can see that in this model the matter goes to 1 and the dark energy goes to 0 at the early time. Fine. So the behavior is right. So this model always go to a matter dominated model in the past. Fine. Maybe a bit slower than the CPL, but it always goes to a matter dominated. So one can actually sort of write this model and add the radiation and use the CMB data with this also. So this model goes to matter dominated model or matter behavior in the past. But at least this data we are only using for the late time behavior.
But as a realistic model, it should also go back to the radiation dominated and even further to the
you can add here with the you can add here the radiation type like lambda CDM also. Lambda CDM also we usually write the lambda CDM model is omega lambda plus omega m1 plus z cube, and we add a radiation part. So we can add a radiation part over here also. There's no problem with that.
But where? Can you just add it in the H of the expression without?
So this is
properly in the scale factor notation.
So for the scale factor, it may be a difficult. One can try to do it, but this scale factor is basically for the late time, and then we get this Hubble parameter, which is basically for the late time. Like this scale factor is basically the lambda CDM behavior at the late time. Then you can add a omega r. So here also in this HZ expression, I can add a omega r 1 plus z to the power 4, so that you can, because this model goes to matter dominated also. And then we can add a radiation part also over here. But the scale factor parameterization, this parameterization is basically just for the late time. Fine. Yes.
All right. Thanks.
So let's thank Anjan again. Thank you so much.
Thank you.